Welcome back to the Deep Dive. Today, we're really digging into something critical, something right at the forefront of AI architecture.
Mhm.
For years, it's been pretty simple, right? The mantra in AI was just bigger is better.
Yeah, absolutely. More data, bigger models, more GPUs.
Exactly. Throw more hardware, more parameters at the problem, and you get smarter AI. That was the idea.
And it worked for a long time.
It did. But we're starting to hit some limits now, like
Yeah.
actual physical walls.
That's right. It's not just theory anymore. We're seeing it in practice. I mean, this push for scale, it gave us incredible things like the current LLMs, advanced vision systems, a lot built on transformers.
Definitely.
And you can see in the data, right? There's been this almost linear relationship between compute and model quality.
Right.
More GPU power, better performance is a
Right.
pretty reliable formula.
Totally reliable.
Yeah.
But like you said, the walls are real. And it gets, well, really interesting here because the constraints aren't just about money anymore. We're talking physics, engineering. I mean, try to picture fitting 1,000,000 top-tier GPUs in one data center.
Yeah, the power requirements alone are staggering.
Exactly. You'd overwhelm most regional power grids. And even if you could power it, what about the heat?
Cooling becomes a nightmare, an absolute engineering challenge.
And then coordinating all those chips.
Mm,
The synchronization time starts to add up.
big time. Plus, reliability, more parts means more things can break.
Right. Single points of failure, data corruption risk. It all just explodes at that kind of hyperscale. It's a really complex problem.
Precisely. And that's just training. Then there's the cost of inference.
Oh, yeah. Running the models.
Exactly. As AI gets integrated everywhere, phones, medical diagnostics, supply chains, the cost to actually use these huge models is massive.
Even tiny fractions of a cent per query add up fast.
Very fast. Billions, maybe trillions annually. So finding ways to cut inference compute isn't just nice, it's essential for AI to be sustainable and widely adopted.
Okay, so with these big challenges, what's next? That's our mission today. We want to introduce you to something genuinely new. Distributed neural architectures, DNAs. And this isn't just tweaking old models. It's a fundamental rethink of how neural nets can be built and process information.
A real paradigm shift.
Yeah, so we'll unpack the tech details, look at how they learn to allocate compute dynamically, and see what their internal structures tell us, especially for vision and language. It's a whole new way of
It
thinking.
really is. It touches on efficiency, interpretability. It's fascinating stuff.
All right, let's really get into the why behind DNAs. We said AI progress was tied to scale for so long. Bigger models, more data, better performance, especially with transformers. It felt almost endless, didn't it?
It absolutely did. The empirical results were just so strong. You had these scaling laws mapped out, showing more compute equals better models. It was, well, pretty compelling.
So GPU use became almost a stand-in for quality. Keep building bigger because, hey, it worked.
It worked incredibly well. It's what got us the amazing capabilities we see today.
But now, these hard limits we mentioned, it's not just the cost of the supercomputer, though that's huge. It's the actual physics.
Right. You physically can't jam 1,000,000 GPUs into one building because of power. Like you said, you'd need the energy of a small city.
And then dissipate the heat. These places are basically giant heaters. You need massive, expensive cooling.
And beyond power and cooling, the engineering gets tricky. Coordinating millions of GPUs, the synchronization delays become real bottlenecks, slows everything down.
It's like trying to conduct a global orchestra perfectly in sync. Impossible.
Pretty much. And then reliability again. With millions of parts, something will fail. A chip, a cable, whatever. And that can ruin a multi-million-dollar training run.
Wasted time, wasted resources. It's a complex system design challenge, not just about raw power.
Exactly. And again, this isn't just training. As AI moves into everyday products, inference costs are a huge factor.
Making it practical, making it economically viable.
That's the key. We need cheaper inference. It's why there's been this big push for efficiency techniques.
Right, things like distillation.
Yeah, distillation, where a small model learns from a big one. Pruning, where you snip out unused connections. Quantization, using less precise numbers.
Speculative decoding too, right? Using a
Right.
smaller draft model.
Exactly, all valuable methods. But they often work after the main architecture is set or after training.
Which leads to another reason for DNAs.
Mm.
This underutilized layer problem. That's a cool idea.
It's a really interesting observation. In standard deep networks, especially for simpler tasks, the deeper layers might not actually do much useful work.
But they still burn compute cycles.
Right, like asking the whole orchestra, as you said, to play just 2 notes, it's inefficient.
Because every input goes through every layer, no matter what. Simple image, complex image, common word, nuanced phrase, same path.
Exactly. Why force simple information through complex machinery? DNAs tackle this directly by learning to choose which modules or layers to use dynamically.
Based on the input itself.
Precisely, it creates an input-dependent computation path, moving away from those fixed, rigid architectures we're used to.
Yeah, that's a massive shift. So let's break it down. What are distributed neural architectures, really? How does this reimagining work?
Okay, the core idea is they are not feed-forward in the standard way, where information goes layer 1, layer 2, layer 3, output.
Right, the pipeline.
DNAs break that pipeline. Information can flow flexibly between any pair of computing modules.
Any pair, wow.
Yeah, think less like an assembly line, more like maybe an intelligent railway network. Each token, like a train, figures out its best route based on what it's carrying.
Okay, I like that analogy. So what are the building blocks of this railway network? What are the components?
So at a high level, you've got two main things. First, the modules, let's call them Maya. These are the actual computation units.
Like transformer blocks.
Could be transformer blocks, yeah. Or simpler MLPs, attention mechanisms, Mamba blocks, even convolutions, the standard tools. The total number of these modules sets your parameter count.
But not necessarily the compute used.
Exactly, because not all modules are active for every input. That's key.
Okay, so modules are the stations or tracks. What's the second component, the train controllers?
Good analogy. Those are the routers, RJ. They're basically classifiers.
Classifiers, how so?
They look at each token, a word piece, an image patch in parallel, and decide which module or modules it should go to next.
Ah, they direct the traffic.
Precisely. The research often used a top K approach. So maybe a token picks the best single module K1 or the best two modules K2 to proceed. And it's dynamic, based on the token's current state.
Okay, so that's the dynamic part. Walk us through how a token actually travels through this network, the dynamic forward pass.
Sure. So first, the input gets embedded, turned into numbers. Then that embedding goes to a router.
Step 1, router decision.
Right. The router picks the next module.
Yeah.
Step 2, computation happens in those selected modules. And here's an efficiency point. If it's an attention module, it only computes attention between the tokens it received, not all tokens everywhere.
Okay, so localized attention, potentially.
Can be, yes. Then step 3, the results, the recomputed embeddings from those modules are brought back together. And the whole process repeats next router, next computation, gather results.
And it's causal. What does that mean here?
Fully causal, meaning each decision is based only on information processed up to that point. Like a detective, you only use the clues you have now, you don't peek ahead. It keeps the flow logical even though the path changes.
That's super clever. The network builds its own computational graph on the fly for each input. And the paper talks about paths and ribbons.
Right. So a path is just the specific sequence of modules a single token takes.
Yeah.
If K1, it's one path.
Simple enough. And ribbons.
Ribbons are for when K is greater than 1. The token goes to multiple modules at a step, so it follows multiple paths simultaneously, like a ribbon splitting and maybe rejoining.
Okay. And the number of possible paths.
Grows exponentially. With the number of steps and modules, the theoretical possibilities are vast.
That sounds complex to track. How do you analyze that?
It is vast. But the insight comes from looking at the emergent patterns. Which paths or ribbons are actually used most often? The paper argues this gives us a new way to interpret the model.
Instead of just activations, you see the strategy.
Exactly. You see the computational strategy the model learned for different inputs. It's like seeing the network's thought process step by step, a big step for transparency.
So the network learns not just what to compute, but how, shaping its own structure based on the input. That's really adaptive.
It is. And crucially, these computation and communication patterns are learned end-to-end during training. They emerge from the data.
Not pre-programmed.
Nope. Depends entirely on the content and context of each token. And you can even shape these patterns by adding goals during training, like optimizing for compute savings or memory use or balancing the load across modules.
That flexibility during training sounds powerful. So this feels very different from standard fixed models. How does it compare conceptually to other ideas out there? Where did the inspiration come from?
Well, the main inspiration goes back to conditional computing. Bengio and others were talking about this around 2013.
Conditional computing. The idea that different inputs take different paths.
Exactly. Instead of one fixed path for everything. The most famous recent example is probably mixture of experts, MOE.
Right. MOE models are great for efficiency. Huge parameter counts, but you only activate a fraction per input. Saves a ton of compute.
Precisely. MOE routes inputs to specific expert networks. DNAs kind of generalize this idea.
Generalized MOE. How?
You can think of DNAs as covering both MOE and also mixture of depths mode, where you skip whole layers sometimes. DNAs go further, creating a sort of mixture of all.
Mixture of all.
Yeah, tokens can take paths of different lengths, skipping not just layers, but even individual parts within blocks, like an MLP or attention part. It also relaxes assumptions about fixed layer order or all-to-all attention. It's much more flexible.
So it's choosing a custom path through different types of units, not just picking an expert. That sounds like architecture search? Is it like neural architecture search?
Yeah.
Very apt.
Good comparison. There are parallels, but a key difference. Traditional NAS finds one static, optimal architecture. You run the search, get a fixed design, and that's it.
And DNAs?
DNAs are more like soft NAS, as the paper calls it. The architecture is determined dynamically based on the input. Different tokens can effectively use different architectures, different parameters, different compute, all decided on the fly. That adaptability is huge.
Static versus dynamic. Got it. What about things like dropout? That also activates subnetworks, right?
Yeah, another useful comparison is to ensembles. Training multiple models is powerful but expensive. Dropout approximates that by randomly sampling subnetworks during training.
Randomly dropping connections or units.
Right. The key difference with DNAs and MOEs, too, is the choice isn't random, it's data dependent. The network learns which path or subnetwork is best for this specific input.
Not just chance.
And there's a fascinating finding. If you look at how often different paths are used in a DNA, it's not uniform, like you'd expect with random dropout. It follows a power law distribution.
Power law. Meaning some paths are used way more often than others.
Exactly. Which suggests a learn non-random prioritization. It's like the model develops favorite efficient strategies for common tasks. It's learned intelligence, not just randomness.
That's a really subtle but important point about the learning and dynamic sparsity. How does routing affect attention?
So routing attention gives you dynamic sparsity naturally. Normally, attention looks at all tokens, expensive for long sequences.
Right, the quadratic cost.
In a DNA, if a router sends only some tokens to an attention module, attention is computed only between those tokens. The others are skipped for that step.
So you save compute by not doing all-to-all attention unless needed.
Precisely. The sparsity pattern depends on the data, determined by the routers. It's another elegant way to get efficiency through learned adaptation.
Fascinating. Learns to be frugal. Okay, let's see how these DNAs actually perform. First up, vision models. What was the setup?
They trained DNA models on ImageNet, the big image dataset, aiming for a scale similar to a VT small model.
VT small, okay. Yeah. Standard benchmark size.
And they used lots of data augmentation, random crops, mixing images, color changes, standard stuff to make training robust and help the model generalize better.
And the big question, could they compete with standard dense models?
They did. Really well, actually. The performance during training pretty much matched the dense baselines, reaching similar accuracy levels on ImageNet.
So comparable accuracy, but potentially more efficient and interpretable.
Exactly. It shows you might not need the whole network firing all the time to get good results.
Which brings us to interpretability. The paper claims the paths image patches take are highly interpretable. What did they find there?
Yeah, this is where it gets really cool. They found clear signs of emergent specialization. How patches traveled revealed a lot.
Like what?
Well, the common paths, the low-rank ones, tended to group patches from different images that shared high-level features, like patches that were mostly sharp edges or big flat areas of color.
So the network learned pathways for basic visual elements, like a visual vocabulary.
Sort of, yeah. And conversely, the rare paths, the high-rank ones, grouped patches from similar images focusing on low-level, fine-grained details.
Examples.
Like, one path might mostly see patches from brass instruments, another might specialize in jigsaw puzzle pieces. It's learning these really specific visual motifs organically.
That's incredible specialization. What about boundaries between objects?
Definitely prioritized. The model learned to pay more attention, route boundary patches differently. Makes sense. Boundaries are key for recognition.
And the most compute-intensive images.
Often the ones with lots of complex boundaries. Like the model knew it had to think harder to segment those properly. It spends resources wisely.
Okay, and this deep dream analysis of paths sounds like visualizing what a path likes to see.
Kind of. It's like activation maximization, but for a whole path. You start with noise and tweak the pixels until the image makes the model strongly prefer that specific sequence of modules.
And what did the dreamt images show?
Really striking results. Optimizing for a path often reconstructed an image semantically similar to the original inputs that took that path.
So the routing decision itself encodes info about the object.
A lot of info. Object type, location, even object background separation. They showed reconstructed peppers, a bird, a dog, clearly recognizable. It shows what the network cares about for routing.
Wow. Did they see a progression along the path? Simple features first, then concepts?
Yes, a very clear progression. Early steps, maybe 1 to 3. The routing was based on low-level stuff like edges. Steps 4 to 6, maybe light-dark patches. Then, around step 7, boom, the object suddenly emerges in the reconstruction.
Like it's piecing it together.
Exactly. Collecting evidence, then synthesizing it. Later steps, 7 to 10, seem to refine details, animal parts, textures. It's a step-by-step view of the processing hierarchy.
Building complexity. And the deep dream with context for segmentation.
Yeah, they found if you provided context, kept the original pixels for a certain group of patches, the object reconstruction got much better.
Implying the routing is linked to segmentation.
Strongly. The model learns to group patches belonging to the same object through its routing strategy. It's like unsupervised segmentation emerging naturally.
Amazing. This all points to efficiency. How does the compute usage look in practice for vision?
It's clearly dynamic. Simpler images like flat backgrounds, less compute. The model recognizes it's easy.
And complex images, textures, boundaries.
More compute. It allocates more processing power where needed for the tricky parts requiring more segmentation effort.
Intelligent resource allocation. What's the overall compute distribution?
It roughly follows a bell curve, a Gaussian distribution. Most images use a moderate amount of compute, fewer need very high or very low amounts. Seems to reflect the dataset's natural complexity mix.
Okay, and beyond compute, there was this other emergent thing, parameter sharing. What's that about?
This is also really interesting. Even without being explicitly told to, the DNAs learned to reuse certain modules.
Reuse, like send tokens back to the same module later.
Yeah, or use the same module for different patches at different stages. It's emergent weight sharing, happening automatically based on the input. Learned recycling.
How much reuse did they see? And did certain images trigger more reuse?
For top 1 DNAs, K1, average reuse was about 25%. For top 2, around 15%. Interestingly, images with high reuse often lacked a single clear object. Attention was spread out.
So if the model couldn't easily focus, it reused modules more.
That's the hypothesis. Like it was exploring or iterating more when the target wasn't obvious, a different processing strategy.
Was this reuse consistent across different models or random?
They found a high correlation in reuse patterns between different trained DNA models. Suggests it's data-dependent, certain inputs naturally trigger reuse, not just a random quirk of one training run.
So it's a learned strategy for certain image types. Now, is module reuse linked to FLOP savings from skipping modules? If you reuse more, do you skip less or vice versa?
Crucially, no. They found no correlation between FLOP savings from skipping and the amount of module reuse.
Really? They're independent?
Seems so, which indicates the model has distinct criteria for saving compute by skipping versus reusing parameters. 2 separate learned efficiency tricks. Fascinating.
That is fascinating. Okay, let's switch to language models. Vision showed amazing adaptability, but language is arguably even more complex, more ambiguous. How did DNAs handle text? What was the setup?
They used a big chunk of the FineWeb Edu dataset, 21 billion tokens. That's comparable in scale to what you'd use for something like GPT-2 Medium.
So a serious challenge. Lots of diverse web text.
Definitely. A much messier, more complex environment than ImageNet. A good test for a new architecture focused on emergent structure.
And how did they perform against, say, GPT-2 Medium?
Very competitive. Their validation loss was right in the same ballpark, sometimes even a bit better depending on the configuration.
That's impressive given the dataset complexity in the novel architecture. Shows the approach is viable for language, too.
Absolutely. It's strong proof of concept. The dynamic allocation works for language. It doesn't inherently sacrifice performance at that scale.
Okay, interpretability in language. Did they find similar emergent specialization, understandable patterns like in vision?
Yes, but with distinct linguistic flavors. The early routers, the first few decision points, learned to group tokens semantically or lexically.
Like grouping similar words.
Exactly. They found one module handling neural concepts and food verbs like dinner, breakfast. Another specialized in punctuation. Another handled word pieces. Others grouped plural nouns or verb forms.
It's like it's building its own internal grammar and thesaurus automatically.
Pretty much. Deciding where to send words based on what they are or what they mean.
Wow. What are the full paths tokens took? Did that show deeper meaning?
Yeah, looking at the path distribution was insightful too. The common low-rank paths often captured common words like linking verbs or words with similar conceptual roles.
Examples.
One path seemed related to actions and targets, another group things related to human endeavors like lock, constitution, declaration, high-level semantic groups emerging from routing.
And that end of sentence path.
Right, the rank 2 path focusing on end-of-sentence tokens. You could interpret that as emergent sentence-level attention, a mechanism to recognize completed thoughts.
Clever. But what about common words showing up in rare high-rank paths? That seems odd.
It does initially. The idea is that when a common word appears in a rare path, it's not about the word itself, but its highly specific, unusual context in that instance.
Ah, so the context makes it special, routes it differently.
That's the hypothesis. The model recognizes all in this very specific context is different from all generally. Shows a deep grasp of contextual nuance influencing the architecture itself.
Profound. Okay, compute efficiency in language. How did the compute distribution compare to vision?
It looked quite different. Vision had that bell curve. Language was more uniform. Most text examples needed a similar amount of compute.
Why there's?
Likely the sheer diversity and complexity of language. Every token, its context, often needs a decent amount of processing. Harder to just skip big chunks compared to maybe a uniform background in an image.
But did they find any content using less compute, like noisy or simple text?
They did. At the lower end of the compute use, they found things like raw HTML code, lots of web links, bibliographies.
Stuff the model might see as less semantically rich.
Exactly. Or text with foreign characters it hadn't really learned, like Arabic or Hebrew, suggests it efficiently processes or filters out what it considers noise or less informative input. Saves compute smartly.
Practical for real-world data. What about parameter sharing in language? Did that happen too?
Yes, module reuse occurred in language DNAs as well, but unlike vision, it didn't seem to correlate with easily identifiable features in the text.
No clear link to specific types of sentences or words causing reuse?
Not in an obvious interpretable way. That was a key difference from vision.
So how did compute correlate with reuse in language then?
There was a strong correlation between reuse and compute used in language models, but the researchers think it's likely just a statistical effect. If you skip fewer modules overall, meaning more are active, the chance of reusing one of those active ones just goes up naturally.
Ah, so it's not necessarily a smart strategy, just probability.
This seems more likely, yeah. Especially since the reuse patterns weren't consistent between different trained language models.
Suggesting it might be somewhat random or arbitrary in language, unlike the data-dependent reuse in vision.
Exactly. Which points to maybe needing different training incentives for language models if you want more meaningful, structured parameter sharing, an area for future work.
Okay, this brings us deeper under the hood. The paper mentions DNAN models, breaking down transformer blocks even further.
Right. DNAN takes modularity to the next level. A standard transformer block has, an attention part and an MLP part, usually run sequentially.
Self-attention, then feed forward.
DNAN breaks those apart, treats the attention subblock and the MLP subblock as separate routable modules.
So the network can choose just attention now, or just MLP, more granular control.
Precisely. Instead of the whole block, pick the specific tool. And the finding here was really consistent across both vision and language DNAN models.
What did they find?
An emergent division of labor. In the early processing steps, the models tended to use more attention blocks.
Makes sense. Establish global relationships first. Figure out how everything connects.
That's the intuition. Get the broad context early, using attention strength.
And later stages.
Closer to the output, they preferred using more MLP blocks.
Suggesting MLPs are for more local, compositional work, refining features once context is set.
Seems likely. Taking the contextualized info and doing more specific transformations. So it's not just skipping, it's choosing the right type of computation, global attention, or local MLP work at the right time.
That's a fantastic demonstration of the flexibility, learned adaptive architecture, choosing the right tool for the job, moment by moment.
It really is. It shows DNAs aren't just about skipping for efficiency. They're learning this intelligent, step-dependent division of labor between different computational primitives. It's powerful self-organization.
Okay, we have really unpacked a novel and, frankly, exciting approach today with distributed neural architectures. We've seen how they tackle AI's scaling limits, Not just by going bigger, but by rethinking operations, dynamically allocating compute and parameters based on the input, learning to be resourceful.
Yeah, and beyond the competitive performance, the interpretability is just remarkable, isn't it? Seeing how they learn to segment images or categorize tokens in ways we can actually understand, seeing the emergent logic, that transparency is incredibly valuable.
Absolutely. This work really opens up a new frontier for AI architecture. Powerful, yes, but also efficient, adaptive, interpretable. Now, something for you, the listener, to think about.
Mm-hmm.
What if models could learn to dynamically decide exactly how much compute, how much thought time to spend on each specific token or part of a problem?
Latent space reasoning.
Of-
Spend more effort on the hard parts.
Exactly. Could that unlock solutions to problems that overwhelm even our biggest models today just because they'd be so much more efficient, focusing resources only where needed?
Or think about DNAs as evolving into super smart data filters, learning to prioritize or discard information based on its actual value or relevance. Imagine the memory and compute savings if they only processed what truly mattered for the task.
It's not just making models smaller, it's making them fundamentally smarter, more resource-aware, pushing closer to truly intelligent systems.
The practical implications are huge. Of course, there are technical challenges in optimizing infrastructure for this dynamic routing, as the research notes. But the concept, the promise of DNAs, it's undeniably compelling.
Definitely a space to watch as AI continues to evolve. For more details on this research, check out our webpage, linked in the bio. We'll catch you next time for another deep dive.